we now want to look at the total amount of energy in simple harmonic motion. All right, and to do so, let's think about a block attached to a spring, and it's resting on a frictionless surface, and I pull the block back a little bit and let it go, and the system's just going to oscillate, right? So it's just going to oscillate about the endpoints. Now, recall that if I have such a system and I start my stopwatch right when I release it at the point of amplitude, maximum amplitude, then my solution is going to be a cosine function, and my leading term, or my leading factor rather, is going to be the amplitude of the system, right? Now, also recall that the potential energy of a spring system is given by 1/2 kx squared, where x is the distance away from the equilibrium position, and the kinetic energy is given by 1/2 mv squared. All right. Now, the total amount of energy in my system is going to be given by the instantaneous sum of my two terms. Okay? But I actually want to calculate what this sum ought to be. If I'm resting on a frictionless surface, should conservation of energy hold? Actually, it should. So what we should arrive at is a result where E is actually constant. The total amount of energy in my system remains constant at all times. So as my object is moving, it's either losing potential and gaining kinetic, or gaining potential and losing kinetic, but it's doing so at a rate such that the total amount of energy in the system remains the same. And that's what we want to show. So to do so, let's look at my potential energy term. I'm going to need to square my cosine term. So my potential energy, U, is going to be given by 1/2 times my spring constant times my x function squared. So I'm going to square a times cosine omega t, which is just going to be a squared times cosine squared of omega t. All right. Now let's look at the kinetic energy. The kinetic energy involves a velocity. So a velocity is a derivative of position with respect to time, and then I need to square it. Okay? So I'm going to take dx dt, and that's going to give me a negative sine, negative a omega sine omega t. All right? And then if I square it, I need to square the entire thing, and this gives me a squared omega squared sine squared of omega t. And so, now what I want to do is plug this into my definition of kinetic energy. Right? So I have 1/2 m times a omega squared times sine squared theta. Okay? Now these two terms look pretty similar. They both have, oops, this should be a squared. They both have a squareds. They both have a trig function also squared. This term has k, and this term has omega squared m. Right? But remember, omega squared is equal to k over m. So omega squared m is equal to k. So I can replace omega squared m with k. So I can essentially write this as 1/2 k a squared sine squared of omega t. So now I want to add my kinetic energy and my potential energy. So if I add these, I'm going to factor out my 1/2 k's and my a squareds. Okay? And so we have 1/2 Ka cosine squared omega t plus sine squared omega t, but cosine plus sine is equal to 1. Cosine squared plus sine squared is equal to 1, as long as the arguments are the same, which they are. So this term disappears. Or again, factor, I should say. That factor disappears, and I'm left with 1/2 Ka, which is a constant. So the total amount of energy in my system is going to be dependent on the spring constant and the amplitude I pull it back. Now again, as the system is moving, it's going to transfer some of its kinetic to potential and some of its potential to kinetic as it's moving back and forth. But if at any instant in time I take a snapshot of both energies and add them up, they should equal this value, 1/2 times the spring constant times the square of the amplitude. So this is the total energy in my oscillating system. Okay, hope that helps, and once again, we'll see you next time.